Hello to lecture 3 on Mech 024. Today we're going to discuss expansion fans. Today I'm doing air monitoring, so the environment's a bit sterile and a bit noisy. There we go. So we're going to discuss expansion fans. So just to give a recap of where we are at the moment. If we have a look to see what our flow structures that we've covered so far, we've looked at normal shock, we've looked at an oblique shock. And if you remember, the notation for the oblique shock was there's a deflection angle delta, a shock angle zeta, M1, M2, P1, P2. And for the normal shock, the relationship between region 1 and 2 is quite explicit. The flow upstream is always supersonic becomes subsonic. For an oblique shock, we have our different terminologies. We have weak shock, or weak oblique shock, and strong shock. Now, weak shock doesn't mean that it's weak. It just means that the flow afterwards is actually supersonic, and strong shock just means the flow afterwards is subsonic. And really, that's a kind of very rough way of describing it, but that's generally the sense of it. There's a little subtlety, but really what you're talking about is the pressure ratio. Now, generally, the solution that you're looking for is going to be the weak shock, but the solution you get depends on the overall constraint problem. There is a tutorial question in sheet 2 where we look at how we do this transition from a weak shock to a strong shock to multiple shocks, as the pressure ratio between the exit and back pressure of an exit jet changes. So that's the first kind of terminology we use, important distinction there. And the second one, which is going to also be important here, is the idea that we have what we call a geometrically constrained pressure constrained one. And what I mean by this is that in the geometrically constrained, you generally know the geometry, so you know the delta value and you know the upstream Mach number, and what then you have to determine is zeta M2 and P2 over P1. For the pressure constraint, which occurs, for instance, at the exit of a jet, exit of a diffuser nozzle, is that we're given what the pressure ratio is. So we know what P2 over P1 is, and we know what M1 is, and then we have to determine what M2 is, and zeta is, and delta is. So we have and classifications are important because they tell us how we approach the problem. Now, for the oblique shock case, what we saw was that there wasn't an explicit relationship between M2 and M1, but rather a functional relationship between all of our key variables. In this case, our variables are M1, M2, zeta, delta, and I'll put P2 over P1, that kind of comes out of it. And so we used, I showed you the use of shock charts in order to solve this problem. And also we can use the very nice shock calculator, compressible flow calculator, which you'll see on Virginia Tech website, and also if you go to Google Play and Apple App Store, then you also see similar types of things. Now, as we've discussed a few times, you kind of lose your intuitive. In order to reinforce your understanding of this and be able to answer the question quickly, I would always suggest you try using the shock charts first, just so you get an idea of what those functional relationships are, because before you start just using the shock calculator. Shock calculator is very quick, accurate, much more flexible. So the shock charts are for diatomic gas, gamma is 1.4, but the compressible flow calculators obviously work for the other cases when we're looking at CO2 and methane and all sorts of other things. So today we're going to look at expansion fans, and there are these three flow structures that we've discussed that if we can combine them, we can start to understand forces on lifting surfaces, inlets to jet engines, exit flow from rockets, shock diagrams and all these things, but we require an understanding of both shocks and expansion fans. The critical part about shocks are obviously that there's a pressure rise. Also the stagnation temperature is a conserved quantity, and so those are the two critical things. And so we're going to look at a flow where the flow isn't being compressed as it hits a wedge, but rather turns a corner in the expanded, hence the word expansion fan. The fans being in this case quite critical because that's the mode by which the adjustment takes place. In contrast, just to flag up what we're going to see, is that we'll use quite a similar terminology that we see here, geometrically constrained and pressure constrained problems. That also crops up. But what we'll see is that the problem is isentropic. And so when we were talking about conserved quantities and reference state of the stagnation reference state, then for shocks we use T0 because that's a conserved quantity, but for expansion fans both T0, P0 and ρ0 are also conserved quantities since it's an isentropic process. So let's see what emerges. So these are just images as we've seen before, and what we've discussed before is the streamlines that go past these obstructions as they move. We've discussed frames of reference, so these are kind of streamlines are drawn in the frame of reference of the moving obstruction. And what we see, or we've had our discussion about, is really these, in the shadow graph, these very regions where the flow structures changes very, very rapidly, and the flow properties, pressure and velocity change over a very short distance. These lighter curves here that you can kind of see, these kind of little small things here, are the bits that are the flow features that we're interested in now. And so what we see is when the flow kind of is deflected by the kinematic consequence of the flow having to go round the boundary, we end up with the emergence of, usually this will be like an oblique shock with a bow wave. If it's, well, I think it's probably quite bluff at the front with something that emerges and looks like a oblique shock at the side, streamlines deflected. And what we see is that the flow has to turn a corner at this stage. And so I've drawn it in a rather crude way. And it is that turn around the corner that generates these weak expansion bands. It's a weak process, hence this scarring that you see is not as pronounced as you have with shocks, but they're much weaker and usually masked, but you can kind of see bits of them over here. Some of these look like shocks, so this is a reasonably good picture because it does show it, but generally the change in the density, because that's what you're measuring for a shadow graph, is usually much smaller. As we've discussed before, I'll just kind of flag out what we're going to be looking at. Before we looked at flows where the flow was compressed, and here we're going to look at flows that turn corners. And like before, you're going to have two types of problems where the flow is turning as a consequence of a pressure ratio, P2 over P1, or turning as a consequence of the geometry. As we've discussed for oblique shocks, steady flows, or even unsteady flows, the streamlines cannot go in and out of the wall, and consequently it must be parallel. The wall itself is also streamlined. There are special cases that we've discussed previously, like stagnation points, where streamlines can be attached. They're topologically quite significant, but not part of our discussion here. But we have these two kind of problems where the flow where the turning is determined by purely the geometry of the corner, or the turning is determined by the pressure ratio. Just to kind of flag up where we're kind of looking at expansion fans, against this idea that I think flows expand, and therefore the pressure is reduced. So P2 is less than P1. So before we start all this, we kind of need to roll back, and then I think if you just recollect for lecture 3, we kind of had this very special solution of two special solutions actually, when the deflection angle is 0, and the two very special cases that we looked at, which is really lecture 1, where we go from region 1 to 2, where we've got deflection angle is 0 and the shock angle is 90 degrees. This was our normal shock. This is one special case, but not the special case that we've been flagged up the last couple of lectures, where also delta equals 0. So also m1 is bigger than 1, m2 is less than 1. And in this particular case, the second case, this is that special solution where m2 equals m1, the streamlines are undeflected, and then there's a shock angle, which we're going to go through the derivation in a minute. And this is that special case that we've discussed. This is an infinitesimal perturbation to the flow. And we're going to be looking, in this particular case, at what that angle is. And actually, what we're going to probably do here is kind of reconcile flows that are locally incompressible to globally compressible. What we mean by that is that, you know, I'm in a room and I move my arms around and I'm in air, there's the flow in my vicinity, because my arms are moving around really slowly, can be treated as incompressible. But when I move my arms around, I'm actually generating a flow perturbation. Very small, very small component of that is that adjustment is propagated as a pressure wave rapidly over distance. Now, if we deal with subsonic flows, then are weakly compressible, and I'm moving very slowly, then actually what I'm doing is I'm always generating a flow perturbation. One way to understand that adjustment is to consider the source that's created as I move along and a sink behind me, and that kind of kinematic consequence can be understood by looking at the wave equation for the movement of a source and a sink. Now, there's a speed of propagation in front of me of the sound wave. So if I'm moving very slowly, obviously the sound wave is moving faster than I'm moving, and so in front of me, there'll be a distance beyond which the flow doesn't yet recognise that I've moved, and obviously that distance grows very rapidly in time because it moves at the speed of sound. And so between me locally moving around in the far field, which is beginning to get feel that flow perturbation, there is a process of adjustment. So locally the flow feels incompressible, but there is a distance away from me where that adjustment is propagating away. Beyond there, we have our zone of silence, the distance over which that perturbation has not reached. Now, as I move faster and faster, what begins to happen is that I start to move faster than the rate at which the perturbation is moving away. And what happens there is these kind of radial dispersive waves start to pile up to create a front. And so this is one way in which we can start to understand weak perturbation generated by things moving around. So this is and if we try to do some analysis on this for something that's moving supersonically, and we say that it's moving with speed u, so over time t the obstacle has moved speed ut, then the wave that's generated initially has only moved a distance ct. And so as we add together these perturbations, they create a nice sharp front, and that has a shock angle. So in the frame of reference of that perturbation, so I'm actually after time t and moving here, and moving when I'm here in my frame of reference, the streamlines are going like that, and the delta is 0, and there's a shock angle. This is a weak perturbation, so m1 equals m2. The angle here is quite important. We give it another symbol. Theta is alpha m, and the sign of that angle is simply ct over ut, which is 1 over Mach number. So the shock angle in this particular case is arc sine 1 over m. We're going to make use of that in our next bit of analysis. This drawing here is really just calculated by me generating a series of growing cylinders and just adding them together in MATLAB and then just contouring that up. So there's nothing special here. You might have a slight tendency to think this looks like waves behind a duck swimming on a surface, and partly you're right. That's how we look at the flow perturbation by a disturbance moving on a free surface. We cumulatively add those perturbations in time. The difference is that the speed of propagation is not independent of wave number. So in this particular case, it's just constant for everything. Like for deep waters, you need a little bit more analysis and method of steepest descents. Very nice bit of classical analysis, worth having a look at, I think. So just a few comments about turning a corner. What we saw last time, as we've seen with shocks and some of the crudeness of the angle of deflection here, it's obviously very steep and exaggerated, but due to the formation of shock, entropy will increase. And if we were to take our shock analysis and apply it to a corner that's the flow turning a corner, then what we would see is that the entropy decreases. And so this isn't physical. And so what we understand by this is that a shock is not the way in which a flow turns a corner. Because if it is, it violates second law of thermodynamics. So how does it adjust? Well, it adjusts slightly more gently, and it adjusts in an isentropic through an isentropic process. And so what we do here is we take this this case of a very weak arc wave or mark line, and to see the consequence of having a number of those together. And what we see is that's able to account for the flow turning the corner. Let's see how that happens. So we're going to consider the flow where the flow expands and the process adjustment. The Mach number will increase due to expansion. Yeah, so the main thing is pressure decreases. Mach number increases. So this is how we do the analysis as before. We use conservation principles. Since it's isentropic, we don't need to go through all of the conservation principles. And so here we have a shock wave where we've got a deflection down. Deflection angle is delta nu, d nu, and we're looking at what happens when the flow is turned. And we're going to apply an isentropic approximation and a small angle approximation. If we want to look at the cumulative effect of turn and fire angle, then what we're going to do is we're going to add together this analysis. So we just start off with a small deflection d nu, and then to look at a turning angle, finite angle of deflection around a corner that you're going to have, then we're going to have to add together those components. Just in terms of notation, upstream, all the angles of shock angles or shock wave angles are relative to the local streamline. So upstream you have an angle of alpha m1, and alpha m1 in this particular case is going to be arc sine 1 over m1, and then downstream the angle is relative to the downstream streamline. And so that's how we're going to do it. So let's look at the first bit. So the first thing is that we, as we saw in our oblique shock analysis, on any kind of analysis, is that the flow tangential to the flow structure is going to be continuous, and so this puts an important constraint on relationship between U1 upstream and U2 downstream. So the tangential component upstream is just U1 alpha cos alpha m1, and downstream it's U2 cos alpha m plus du. We're going to use a double angle formula, and as you know, cos a plus b is cos minus sine. small angle, so d nu is a lot smaller than 1. D nu is in radians, so d nu is a lot less than 1, so cos d nu is equal to 1, and sine d nu is equal to d nu, and together this double angle formula ends up being something of this form. I mean, what I'm just missing here is d nu, which is about equal to 1, and then that's sine d nu, which becomes d nu, and that's why we end up with this approximation. And so what this allows us to do is try and calculate or estimate what the fractional change in velocity is between the left-hand side and right-hand side. And since we know the relationship between sine of the shock angle, Mach wave angle, and Mach number, then we can rearrange this fractional change in velocity in terms of Mach number squared. So here we're using the conservation of momentum parallel to the shock wave. Our aim is actually to try and find a differential relationship between m squared and deflection angle. So in the previous slide we found a relationship between du and changing velocity, fractional velocity, and changing angle, and now we need to find a relationship between d nu and dm squared, m squared. So first thing to do, appeal to conservation of energy. As we said before, T equals 1 plus half gamma minus 1 m squared equals constant. That's our stagnation temperature. So we can get rid of eliminate the temperature by writing the fact that u squared over m squared is equal to speed of sound, which is gamma RT, and so we can express T as a u squared m squared 1 over gamma RT. Substitute that in, gives us, I'm taking the square root, gives us this functional relationship between u and m as a constant. And what do we do in those scenarios? Well, we're looking at fractional differences. So one way to convert this functional relationship between u and m is to take the logs. Now it's a kind of trick that we met in year 1 when we're looking at errors in experimental measurements and errors in estimation, where we've got a functional relationship between a number of variables and we want to find out the differential relationship between them. And so one way to do this is we can take the logs, which we do here. So the log of the ratio of u to m gives me log u minus um, and then since this is raised to the power half, the half comes down when we take the log, and that becomes 1 plus a half, and that's equal to constant. And then what we do next is we take the differential of that. Differential of log u is just du over u. Differential of m is log m is dm over m. Differential of this is obviously the differential of the top divided by the thing on the bottom. Differential of this, because it's got an m squared, that brings a 2 down, which cancels with the half, and that gives me gamma minus 1 m dm. Don't forget the dm. M squared. So that's where we're aiming to get a differential relationship between dm squared and d nu. So as I've discussed, taking the log of m and taking the derivative, and the log of u and log of m, and the log of this quadratic in m, gamma is a constant. All this comes together to produce du, which is dm over m times this. And the previous slide, 2 slides before, we had a relationship between du, u, d nu, and so combining those two together, we get to the stage where we know how the fractional change in Mach number, or change in Mach number, relates to the deflection angle. Once we do that, you can see now we've got our two formula relating d nu to dm, and so there, when we have the equality in the middle, and we can now relate the change in the deflection of the flow, the deflection of the streamlines in radians, in terms of the change from Mach number m1 to m2. And so this is good. If we know what the initial Mach number is, m1, yeah, and we know what the change in delta nu is, because if it's a geometrically constrained problem, we know what that deflection is going to be, yeah, then we can calculate what M2 is. Obviously the challenge here is that we would have to have a table with both mark number 1 and mark number 2 and the deflection angle, and that basically becomes a bit complicated. So what we do, and you'll see this a feature through but most of complex fluid mechanics, is we take a reference state, and in this particular case we take the critical reference state, or the sonic reference state, of mark number 1. So although we're going to be looking at something transitioning from mark number 1 to mark number 2, in terms of tabulating the information, we usually use a reference state that might be observed or might not be observed, which is a reference state of mark number 1. So when we come to apply this, and we'll discuss a bit more next slide, we use a standard set of tables where we use a reference state of 1. So yeah, we take a reference state of 1, and we can see how this kind of works, this reference state of 1, if we use the example that we have a flow that starts off with mark number 1.6, and we have a deflection angle of, in this particular case, 20 degrees. And so if we take a reference state of 1, then we end up with this reference state curve on this Prandtl-Meyer expansion chart. Shows the universal solution that tells us the deflection angle nu as we go from a mark number of 1 to the mark number M1 that we want. Obviously we don't start with a mark number 1, we start with something else. So what we do is quite simply, if we're asking a question, we start with mark number 1.6 with deflection angle of 20 degrees. Ask ourselves what is M2 after the turning or the expansion. Then what we do is we take our 1.6, we go up, we ask ourselves what the equivalent initial turning angle would be. In this case it's about 15 degrees. We add 20 degrees on that to take that point up, and then we interpolate back on the curve, and then that tells us our mark number at the end, and that mark number at the end is 2.3. Now the flow in this particular case is isentropic, and because it's isentropic, we have our functional relations between P0 and 1 plus a half gamma minus 1 m squared. And I always forget the numbers, but it's as the mark number goes up, as the mark number goes up, P0 goes up. So it's I think it's minus gamma over gamma minus 1. We can check that. I always forget that kind of. Now the graph below shows a functional relationship between P0 and mark number. Oh yeah, we see. So that tells us that it must be negative. And as you see, as the mark number increases, the pressure decreases rather rapidly. And so in order to make use of this table or this chart, what's plotted on here is the curve itself and 10 times the curves and 100 times the curves, so that you can interpolate at the various points. So if you were to interpolate 2.5, for instance, you get a value of about 0.6, but that's quite difficult to read, so go all the way up to the next one, make it easy to see. 6, and then we divide by 10, so that gives us 0.06. So P, if we did it with 2.3, 2.7, so, and P over P2 over P0 in this case will be 0.0. 6, 5. But this is very rough. The charts are quite good just to get that kind of intuitive sense of what the values kind of mean, but there's little practice in applying them. The calculator is you have to keep on checking, thinking yourself whether the answer is appropriate or not, or whether you've made a mistake. So I would just get used to using the shock charts, the expansion charts in this particular case. So this is the question discussed again, where we start off with a Mach number of 1.6 and we have a turning angle of 20 degrees. We ask ourselves, what does this chart tell us? And this chart tells us what the turning angle would be if you started with a Mach number of 1. And so to apply it to our problem where the Mach number isn't 1, we take our 1.6, we go up to this curve, find out the equivalent initial turning angle, done our 20 degrees, come back down and find M2. In this case, M2 is going to be 2.31. In many cases, you're asked to label your diagrams with the shock angles, shock wave angles in this particular case, and then so these are arc sine 1 over M1, arc sine 1 over M2, and usually you're asked to draw these on top. For expansion fans, as we said, the stagnation, the flows are isentropic, so P over P naught is given as a function of M. It's constant across the fan itself, and so and that's we need to make use of that when we do our calculations. So if you do your calculations here, you know what P1 over P naught is going to be, in which case let's just see that was 1.6. Let's say that gives you a value of 0.02 gives you a value of 0.24, and P2 over P naught, since P2 is going to be about 2.3, take 2.3 up to here, that's going to be 0.065. What we're really interested in is P2. So P2 is actually P2 over P naught times P naught over P1 times P1. So we know P2 over P naught, 0.065. We know P naught over P1, that's 0.24, and we know P1. So if we know those pressure ratios, we need to multiply them in a sequential way in order to eliminate P naught and determine what P2 is, and that's how you calculate your change in pressure, noting that P naught is a conserved quantity or is constant across the this solution admits a maximum deflection angle, and so which is just given by a functional relationship between a strong dependence on gamma. And so for flows where the deflection angle is larger, obviously how does the flow accommodate? Well, it's easy. What it creates is a slip plane, and the slip plane is where the flow essentially has an adjustment from a region which is stagnant, stationary, and a flow that is moving. And obviously for those types of flows you'll end up with, you tend to see vortices and interfacial shear that are really quite pronounced. So how does the flow adjust? Well, as we've discussed, if the flow is turning up or it's compressed, the shocks form, and if it turns a corner, we have an expansion fan, a series of waves that are emitted at the corner, these very small infinitesimal arc waves, and this allows the flow to be deflected. So in the So we've covered expansion fans, oblique shocks, normal shocks. So what we're going to be doing next is we're going to be trying to wrap or combine that information to look at forces on aerofoils, where we're combining oblique shocks and expansion fans. So let's see how that unfolds next.